So, my name is Emiliano Maretes, and I will explain the project we did with my team. And first, I'm going to answer the question of provide a brief explanation of your project, the objectives, and deliverables. Then, explain the setup for collecting the damping ratio, materials, geometry, loads, data, collected formulas used to analyze the data, and why this data was needed and how this data was used for the solution of the project. And I'm also going to answer the question of explain your simulation procedure, what is the purpose of the simulation, describe your FEA model, what results were obtained, and how are you going to use these results. Okay, so first we have for the project, we had to use two materials, that was onyx and TPU. And with these two materials, we had to obtain first the damping ratio. And for this, we had to use the logarithmic decrement equation that we used, that is the natural logarithm of the first peak divided by the second peak. And with this damping ratio, we could obtain the damping coefficient. But for the damping coefficient, we had to obtain distinct formulas. For example, first we had to use our FEA model, and with the FEA model, we had to apply a load in one end, and the other was like a cantilever beam. And with this cantilever beam, we could obtain the theoretical K by analyzing the displacement, and with the displacement, we could use the equation for K, and with this K, we could obtain the critical damping coefficient. That is the equation for the damping coefficient. That is the damping ratio times the critical damping coefficient. And with this with the damping coefficient, we could simulate our leaf spring with the particular geometry. And so this geometry that we used is really important, because the geometry of our leaf spring, we could obtain the moment of inertia, mass moment of inertia. And with this mass moment of inertia and the particularities of our material, we could obtain a theoretical K that we could contrast with the K we obtained with the FEA model. And so once we obtained the theoretical and the analytical Ks, we could contrast them and determine which one was better to use for our model. And in our case, the differences between our theoretical K and the one we had in the FEA, it was less than 10% of error. And so we decided to use the FEA one because it was more precise in the particularities of our shape. And so this is in particular with the geometry of our leaf spring, that it was a rectangular prism. And so for the loads, we had to apply a load that was less than 20 newtons, because if it was more than 20, it would surpass the limit of elasticity. And so in our case, I think it was 10 newtons, the limit. So we applied a load of 10 newtons in this case. And so the formulas we used are the ones that I already explained. And this data was needed to obtain both the K and the C. And once we obtained these two values, it was time for us to make a model out of this. And so we made a model based on the particularities of the shape of the vehicle. And so we just we put it the road, and then we used a spring and a damper to put it right beside the leaf spring, and then to the vehicle, simulating the bouncing and the damping of both leaf spring and the vehicle. And so lastly, what is the purpose of the simulation? It was to obtain the K. To obtain the K, we need to do the simulation that I already explained. And so the conclusion for this was that the results are really conclusive. We got what we needed, and I think it's really important to simulate further analysis on the leaf spring. Thank you.